Thank you to the organizers for giving me this opportunity to talk today. I apologize to those of you who are coming from Benasque because this is probably just going to be a repeat of what you heard there. Today I'm going to be telling you about this paper I put out about 2 months ago, which is related to some of the topics you heard, or ideas you heard from Misha yesterday, about including observers in closed universes and how we deal with that when we use the gravitational path integral to calculate things. So to quickly review some of the ideas that Misha introduced, let's recall some of the lessons we learned about the black hole information paradox over the past couple of years. Recall that this puzzle concerns the fact that if we naively calculate the entropy of Hawking radiation emitted from an evaporating black hole, this thing seems to increase monotonically. However, as the black hole evaporates, the number of states of the black hole should decrease, and we expect the log of this number of black hole states to bound this entropy of the Hawking radiation from above. So there seems to be this tension from what we expect versus what we get from the calculation of the Hawking radiation's entropy. What we realized in recent years is if in the gravitational path integral we sum over different topologies, then we are able to resolve this tension. In particular, suppose we want to compute, say, the second Renyi, or the swap entropy of the Hawking radiation, with two replicas of my black hole. So this is preparing the ket of one replica, this is preparing the bra of the same replica, and I have two of these. When we use the gravitational path integral to compute Renyi entropies, we include not only topologies which connect the interior like this, but also topologies which connect the interiors in this sort of crossed fashion. Then the result that we find for the entropy of Hawking radiation is that it follows the Hawking answer up to what's known as the page time, and afterwards it follows this bound from the number of black hole states back to 0. Okay, but now if we apply the same set of rules for the gravitational path integral now to closed universes, as Misha told us yesterday, we come to the surprising result, what that means is if we try to use the gravitational path integral to compute inner products for closed universes, say prepared by these boundary manifolds, and we include all topologies, so topologies which look like this, and analogous to this kind of topology, we also include these cross terms, then we find that the gravitational Hilbert space for closed universes is one-dimensional. Now, over the past couple of months, there have been at least 2 prescriptions, probably more by now, for how to deal with this by including observers in the gravitational path integral. All of these prescriptions include some extra ingredient or some modification to the gravitational path integral when we try to include these observers. So one of these prescriptions is by the Berkeley group. Stefano is not here right now, but it's by Stefano and other authors from Berkeley. And in this prescription, when we include an observer, what that means is when we compute inner products for, say, states prepared on these boundary manifolds, what we need to do is include an observer world line which connects a given boundary manifold preparing a ket state to the corresponding boundary manifold that prepares the corresponding bra state. With this prescription, these authors find that the dimension of the closed universe Hilbert space is no longer 1, but instead it scales something like e to the 2s naught in JT gravity. In higher dimensions, we expect that this 2s naught is going to be replaced by something like a over 4g, where a is some extremal surface surrounding the observer. If the observer has d many internal states, then this also comes with a factor of d. So this is one prescription for including observers, and which gives us a non-trivial Hilbert space for closed universes. Yesterday, we also heard Misha talk about his distinct prescription for including observers. And in this prescription, or you can think of this prescription as being implemented by introducing this extra ingredient, this external clone, which is some external non-gravitational system, which is required to be entangled maximally with the internal state of this observer. I should say that this prescription, or the treatment of the observer in this prescription, is distinct from the previous one in the sense that this observer world line is treated like any other matter world line. By that I mean this observer world line can connect, for example, directly from the ket to the corresponding bra, or it can connect to something else entirely. This is how you would normally treat matter, or matter world line, or okay, maybe I should just say matter modeled as world lines. Okay, so with this prescription, what these authors instead find is that while the closed universe Hilbert space is not 1, it now scales like the minimum of D, where D is the number of observer internal states, and e to the 2s naught in JT gravity. So we see that these prescriptions are not only distinct in the way they implement or modify the gravitational path integral, but they also give qualitative or quantitatively different results. Now in this talk, the goal is not to try to start a fight over whose prescription is better. Instead, I'm going to try to describe a general, a general framework which tries to isolate or pick out the key features of these prescriptions which lead to the non-trivial Hilbert spaces. This general framework is going to be an extension of previous work, which started in the 1980s. There we go. In the 1980s, by Coleman, Giddings, and Strominger about baby universes and alpha states, and which recently sort of resurged because of a paper by Merolf and Maxfield in 2020. This will also be an extension of some work by some UCSB folks about treating the gravitational path integral abstractly. Using this framework, I'm firstly going to review why one-dimensional Hilbert spaces are associated with closed universes. And then I'm going to explain how non-trivial Hilbert spaces arise when we consider universes with spatial boundaries, and also when we consider these newer prescriptions for including observers in closed universes. So this is the outline of my talk. Before jumping in, maybe let me pause to see if there are any questions. Yeah.
Sorry. Perhaps I was not in asking, so perhaps a too simple question. Yesterday in the Misha talk, I also saw these alpha states. Now you mentioned them again. I'm not very familiar with what you're talking. Are these the seated alpha states? What is the idea behind this? Like a multiplicity of vacuum is what you're saying?
There's a sense in which it's a multiplicity of different vacuum, but I think you might also think of it as different theories altogether. I'll actually explain this whole framework of baby universes and alpha states, so hopefully that will become more clear.
Okay, thank you. Sorry.
Awesome. So let's jump right in now. I'm going to start by describing the gravitational path integral very abstractly as just some function which takes an input, something which we'll refer to as a source, and maps it to a complex number. So what are some examples of these sources? One example would just be a boundary manifold. This may very well just be the empty set, in which case you can view the path integral as summing over different bulk configurations with no boundary at all. This boundary manifold can also be non-trivial, and it's going to specify some boundary conditions that our bulk configuration must satisfy. Then the path integral you can view as just summing over different bulk configurations which satisfy those boundary conditions. Now, given two boundary manifolds, we're also allowed to take their disjoint union. There are two things I want to point out here. Maybe before getting to that, the way to think about this is that now if we evaluate the path integral on this disjoint union, that's just going to sum over different bulk configurations, which satisfy the boundary conditions specified both on M and M prime. Okay, so there are two things about this that I want to point out. The first is that I'm going to treat this disjoint union as a commutative multiplication operation. What that means is if I swap the order of M and M prime, I'm going to define that as the same as if I took the disjoint union of M prime with M. Implicitly, what that means is the path integral is going to be blind to this ordering of sources and disjoint unions, right? It's not going to care whether I've drawn it this way with M before M prime or the other way with M prime before M. The other point I want to emphasize is that because when we sum over different bulk configurations, that's typically going to involve these connected wormhole geometries, our path integral is not expected to factorize into pieces associated with each piece of the boundary manifold. So one way to say this is just, as I said, the path integral does not factorize. That's what I mean. Okay, later when we talk about observers, it'll also be useful to consider these sources which are comprised of boundary manifolds connected by some geodesic. This is going to be a geodesic which travels through the bulk. So what this source is telling you, or instructing the path integral to do, is to sum over all bulk configurations which satisfy the required boundary conditions on M and M prime, and also contain this geodesic. Later on, we'll see that this geodesic has the interpretation of an observer world line in some prescriptions. The next thing we allow is superpositions of sources. That means I can take an arbitrary collection of, say, boundary manifolds, and I'm allowed to consider complex superpositions of these boundary manifolds. This might seem a bit strange, but momentarily we'll see that this has the interpretation of preparing a superposition of gravitational states. For now, though, you can just define this superposition as an instruction to evaluate the path integral on the source appearing in each term separately, and then adding the result in the end. So that's going to define what I mean by a superposition of sources. The last structure that we require is for there to be a star involution on this set of sources. You can view this star involution as taking a complex conjugation and time or orientation reversal of the source. Practically what that means is if I have a boundary manifold, which I'm viewing as preparing some ket state of a closed universe, then there's going to be a corresponding boundary manifold, M star, which prepares the corresponding bra state. To summarize everything I've said on this slide, I can simply say that the set of sources has the structure of a commutative star algebra. Let me break that down. The algebra just means it's a vector space, and it has a multiplication operator, or operation. This multiplication is commutative. And finally, the star here just refers to this complex conjugation and time or orientation reversal of a source. Moving forward, we're actually going to use this property as an abstract definition for what I mean by a set of sources for the gravitational path integral. Okay, now let's use this set of sources to prepare a Hilbert space of closed universes. So the idea here is that each source is going to prepare a state in a closed universe Hilbert space. So in the example where I'm considering a boundary manifold, you can imagine that this boundary manifold is inserted somewhere in the Euclidean past, and this is going to prepare a gravitational state for a closed universe. Away from this boundary manifold, this closed universe is typically going to have arbitrarily fluctuating topology, and its local field configurations are going to vary freely across different configurations. That's going to appear in the path integral. We're going to refer to these freely fluctuating closed universes for historical reasons as baby universes. Now, on the previous slide, I've already described how this set of sources has the structure of a vector space. To turn this into a Hilbert space for this closed universe, I also need to give you an inner product. And to do so, I'm going to use the gravitational path integral to define such an inner product. For example, if I have a ket state prepared by some boundary manifold M, and another state prepared by a boundary manifold M prime, to compute this inner product, what I do is I firstly take the star of M prime, so that's going to prepare the corresponding bra state. I'm going to take the disjoint union of that with M, and then ask the path integral to fill in everything in between. The value of this path integral is going to define what I mean by this inner product. And to have a consistent theory, I'm just going to require this to be a positive definite inner product. So this is how we view sources as preparing states in a baby universe Hilbert space. We can also view these sources as operators acting on this Hilbert space. So given a source, I can define an operator Z, which acts by taking the disjoint union of J with the state. So let me illustrate that. Suppose I have a state prepared by some boundary manifold M prime. Using another boundary manifold M, I can define an operator Z, which acts on the state by simply taking the disjoint union of M and M prime. So the result now is just going to be a gravitational state prepared by the disjoint union of M and M prime. Regarding these operators, I have two observations to make. The first is that the adjoint of one such operator is given by the star of the source. This follows straightforwardly from this definition of the inner product. The second observation is that these operators all commute with each other. And that follows immediately from the fact that disjoint union is commutative. So to summarize, what we find is a commutative star algebra of these operators Z, which can therefore be simultaneously diagonalized. Or said another way, the adjoint of each of these operators is another Z, and we know that all Z's commute with each other. Therefore, these operators Z are normal, and so we can simultaneously diagonalize them. So let's do that. What we find then is that our baby universe Hilbert space decomposes into simultaneous eigenspaces for these operators Z. So written as a formula, our baby universe Hilbert space decomposes into a direct sum or integral over these sectors labeled by alpha, where each of these sectors is the simultaneous eigenspace of all of these operators Z. So in each such sector, this operator Z takes a definite value Z sub alpha. These eigenspaces have a name, and that's an alpha sector. So, okay, there are three things I want to comment about these alpha sectors. The first is that each alpha sector is one-dimensional, meaning it's spanned by a unique state. So to see this, we can consider any such alpha state in a given alpha sector, and consider its inner product with an arbitrary other state prepared by an arbitrary source. We can express this as a matrix element for this operator Z, acting on the Hartle-Hawking state, because the disjoint union of J with empty set is just J. Now, because this operator Z is an eigenstate of this alpha, I can simply pull it out of this between these states as the eigenvalue of this operator Z in the eigenstate alpha. Okay, now from this expression, it's straightforward to show that any two such alpha states in the same alpha sector are actually linearly dependent on each other. So it follows that each alpha sector is one-dimensional. The second comment is kind of trivial, and that's just that each alpha sector is a superselection sector, which is preserved by all of these operators Z. That's almost by definition, because these alpha sectors are the eigenspaces of these operators Z, so obviously they are preserved by the operator Z. Because they're superselection sectors, I might as well think of each alpha sector as the closed or baby universe Hilbert space of an independent theory. right? If you're already in an alpha sector, then acting with these operators Z is not going to move you to a different alpha sector. So I might as well associate each alpha sector to an independent theory altogether. Now in each such theory, this is sort of a side comment, in each such theory we actually have a factorizing path integral. I make this comment to relate this to sort of what we expect in standard ADS-CFT when we have a single CFT dual. In that case, if we evaluate the CFT partition function on, say, the disjoint union of two boundary manifolds, we expect that the partition function is just going to factorize between the two pieces of the boundary manifold. So in each such theory, we have this factorizing path integral. Meanwhile, the original path integral is actually an ensemble average over these individual, these partition functions for these independent theories. To see this, we can express our original path integral as an expectation value of this operator Z, and then we simply insert, or say this is the expectation value in the Hartle-Hawking state, and we can simply insert a complete basis of these alpha states, and that turns this expression into just an ensemble average over these Z sub alphas with weights given by this overlap between the alpha state and the Hartle-Hawking or no boundary state. Okay, so I know that there's lots of text and formulas on this slide, so let me just highlight the key points here. The key point is that each alpha sector is one-dimensional, and you can think of it as the closed or baby universe Hilbert space of an independent theory. So that's what more precisely people mean when they say that closed universes have one-dimensional Hilbert spaces. Yeah.
Where do you use here that the universe is closed?
That is because these states are prepared by these complete sources. So meaning if I take, so because they're complete sources, you can think of it as being completely inserted in the Euclidean path, and there's not going to be any intersection with some, say, initial time slice. I'm going to describe a situation in which we're preparing states for open universes, and I think it'll become more clear there. Right, so in fact, that's the next slide. Okay, so here we've seen how these alpha sectors for closed universes are one-dimensional. The question now is, how do we get non-trivial alpha sectors? Now, as I said on the previous slide, each alpha sector in standard ADS-CFT you can think of as being associated with a single CFT. But we know that each CFT actually has many states. So how is that consistent with what I just said? Well, let me be a bit more precise. We know that each CFT on a d-dimensional boundary, or d-dimensional boundary manifold, has many states living on any d-1 dimensional cut of that boundary manifold. In the CFT, we can view all of these states as being prepared by, say, CFT path integral on a partial boundary manifold, itself with boundary given by this cut, which I'm going to call sigma. Different choices of this partial boundary manifold is going to prepare different states for the CFT on this cut sigma. Now let's look into the bulk. What we see is that these states of the CFT are not dual to closed universes, but rather open universes with spatial boundary sigma. So here in this example, I'm preparing, say, a thermofield double in the CFT, and this is dual to an asymptotically ADS black hole with ADS or asymptotically ADS boundary sigma. Okay, so coming back to Dimitri's question, this would be an example of something you would use to prepare an open universe state. And the distinguishing feature here is that these partial boundary manifolds have this cut, whereas a complete boundary manifold does not have such a cut. Okay, so the idea for the rest of this talk is to generalize these ideas. So in the same way that we define these sources as an abstract generalization of boundary manifolds, in the rest of this talk, I'm going to, in the next part of this talk, I'm going to abstractly define these partial sources as a generalization of these partial boundary manifolds. Yeah.
Is the fact that the alpha sectors are one-dimensional, is it not simply a consequence of you assuming the commutativity?
Yes, that is the key ingredient which gives you the one-dimensional alpha sector.
Okay, so, okay.
It might be useful to also enhance the answer to Dimitri's question and combine it with this one by mentioning that at the axiomatic level, the difference between the sources with no cuts, the complete ones, the partial sources with a cut, is that if there's no cut, the only multiplication thing you can do is the disjoint union, which is commutative. Whereas if you've got a cut, you can attach things in a sequence and it's not commutative. So those things are deeply connected.
Yeah, yeah. We'll actually see a nice picture of that in later slides. Okay, right, so the main point of this talk is going to be the fact that if we prepare states using these partial sources, they're going to form Hilbert spaces whose alpha sectors are now no longer going to be one-dimensional. That's sort of a generalization of what we saw up here. Okay, so getting right to it, what I'm going to do now is define what I mean by a set of cuts and sets of partial sources. To do so, I'm just going to go through each abstract structure that I'm going to require for this set of cuts and these sets of partial sources. Along the way, I'll also draw some pictures which will hopefully ground these sort of abstract ideas in the example in which we are considering partial boundary manifolds. Okay, so at the outset, the set of cuts is literally that. It's a set whose elements we're going to call cuts. For each cut, there's going to be a corresponding set, script JC, of elements which I'm going to call partial sources with cut C. Now the first structure that I require this set of partial sources to have is that of something like a vector space, where these sources, okay, so these are complete sources, the same kind that we talked about earlier in this talk. These complete sources play the role of scalars. What on earth does that mean? That means if I have a partial source, I can do a scalar multiplication, which is this disjoint union, with a complete source. Given two partial sources, I can also add them together. Might be helpful to look at a picture. So if I have a partial boundary manifold, I'm allowed to take its disjoint union with a complete boundary manifold, that's scalar multiplication. And I'm also allowed to take arbitrary superpositions of these partial boundary manifolds. So that's what I mean when I say this set of partial sources is like a vector space where these complete sources play the role of scalars. There's sort of a fancy math word for this, and that's a J module. Now, if you don't like fancy math words, in the following, every time I say J module, just think vector space. Just like for vector spaces, we're allowed to take tensor products. We're also going to use the same O time symbol to denote a non-commutative multiplication on this set of cuts. Now, this is sort of hard to digest, so I'm going to suggest the following conceptual interpretation of this symbol. You can view this symbol as a disjoint union, except now ordering is going to matter. So if I want to consider the tensor product of this partial boundary manifold with another partial boundary manifold, you can think of it as just a disjoint union. But for reasons that I'm going to explain on the next slide, the ordering of n and n sigma prime is going to matter. Okay. Now, with respect to this multiplication operation, this ordered disjoint union, if you will, I'm going to require this set of cuts to have an identity element. For this trivial cut, I can simply identify the set of partial sources as a set of complete sources. Right? In terms of boundary manifolds, a boundary manifold with a trivial cut is the same as a complete boundary manifold. Lastly, on this slide, we also require there to be a star involution, which we can again view as taking the complex conjugation of any data specified, say on these boundary manifolds, and the time or orientation reversal of that boundary manifold or partial boundary manifold. So for example, if we have a partial boundary manifold which prepares some cat state, there's going to be a corresponding partial boundary manifold, N star, which prepares the corresponding bra state. Okay, so on this slide, I'm going to define what I think are probably the more important structures that I require for these partial sources. In particular, we require there to be a gluing operation. So consider a partial source, which has lots of cut components, and in particular, it has cut component C and another component C star. I require there to be a gluing operation, which lets me glue together C and C star. If I do that, then I'm going to get a new partial source, which no longer has these cut components C and C star. Okay, so this is sort of like tensor contraction, if you will. If you take a bunch of tensor indices and you contract two of the indices together, you're going to get a new tensor which no longer has those indices. Just like for tensor indices, you can also introduce a swap operation, but actually for this talk, probably this isn't too important, so I'll just gloss over that. What is important is that using the star involution that I defined on the previous slide, and this gluing operation, I can now define a Hermitian form. So in terms of pictures, to evaluate this Hermitian form onto partial boundary manifolds, we can view it pictorially like this. What I do is I first take the star conjugate of the first partial boundary manifold. So that means I take any initial data on here, and I take its complex conjugate, and I take the time or orientation reversal of this n prime. So that's going to give me this n prime star. Next, I'm simply going to glue this partial boundary manifold to the second partial boundary manifold along the cut. So the result now is just going to be a complete boundary manifold. So what this Hermitian form does is it takes as input two partial sources, and it spits out a complete source. So in this example, two partial boundary manifolds, and the result I get is a complete boundary manifold. Okay, now let me take this opportunity to explain why ordering matters in tensor products. Suppose we evaluate the Hermitian form for n1 times n2 with itself. The result you're going to find is simply going to be n1 glued to n1 star and n2 glued to n2 star. However, suppose now I swap the ordering of n1 and n2. So okay, ignore this first expression. I've simply swapped the ordering of n2 and n1 and n2. So now it's n2 and then n1. Now if I evaluate this Hermitian form, what I find is a different result, which is that n2 is now glued to n1 star, and n1 is glued to n2 star. Okay, so this is why ordering matters when you take these tensor products of partial sources. Now, using these partial sources, we can again define or construct a Hilbert space. The idea, as before, is that each element, so in this case, each partial source, is going to prepare some state in a Hilbert space labeled by this cut C. We already saw on previous slides the example in which we're considering partial boundary manifolds, which prepare states in the Hilbert space of open universes with boundaries sigma. Now, like before, I'm going to use the gravitational path integral to define the inner product on this Hilbert space. To do so, what I do is I take the two, say I have two states prepared by these partial sources. To evaluate this inner product, what I do is firstly take the Hermitian form of these guys, so that's this thing here, and then I evaluate the path integral on the complete source given by this Hermitian form. So in terms of pictures, if I have a partial boundary manifold preparing some open universe state, and another one preparing another state, to evaluate this inner product, what I do is I first take the star of n prime, I glue it to n, so that gives me the Hermitian form, which is a complete boundary manifold, and then I plug that into the path integral, and the value of that path integral defines this inner product. As before, I require this to be positive definite. Now, okay, just like before, for each complete source, this is going to define an operator Z which acts on this Hilbert space. It's going to act basically exactly as before by taking the disjoint union with J. So for example, if I have a state prepared first by some partial boundary manifold, I can define this operator using a complete boundary manifold, I can define this operator Z, which acts on this state by simply taking the disjoint union of M and this partial boundary manifold N. The result in the end is just going to be a new state prepared by the disjoint union of M and N. For the exact same reasons as before, these operators are going to form a commutative star algebra of operators. Again, they're commutative because these operators act by disjoint union, so they're going to commute with each other. And moreover, the adjoint of one of these operators is just another one of these operators. So all of these operators commute with their adjoint, and so they're normal. Therefore, we can simultaneously diagonalize all of them. So let's again do that and see what we get for the alpha sectors. What we find is that our Hilbert space is again going to decompose into these simultaneous eigenspaces for these operators Z. So again, each of these eigenspaces is going to be labeled by some parameter that I'm going to call alpha, and in each of these sectors, my operators are going to take definite eigenvalues Z sub alpha. I can say mostly the same words as before. Each of these eigenspaces are what I'm going to call an alpha sector, and they're superselections with respect to these operators, obviously, and therefore we can associate them to some independent theory of gravity. However, one thing that's going to be different is that these alpha sectors are no longer going to be necessarily one-dimensional. Instead of reviewing the previous argument and showing why it no longer applies to this case, I think it would be more instructive in this case to just construct for you an algebra of non-commuting operators acting on these alpha sectors. Obviously, to support non-commuting operators, these alpha sectors then have to be greater than one-dimensional. I think this is more instructive because it illustrates the fact that in quantum gravity, in order to define non-trivial operators, you sort of need objects to which you anchor or dress these operators to. And that's what these cuts do. They're places to which you can dress such operators. In fact, we're going to define now operators which literally glue onto these cuts. So to that end, let's consider a partial source with two cut components, C and C star. Using this partial source, I can define an operator which acts on states by gluing C star to the state. So something like this. Again, it might be helpful to look at a picture. So consider a state prepared by some partial boundary manifold. I can define an operator using another partial boundary manifold, which has cut components sigma star and sigma. And this operator is going to just act on the state by taking sigma star and gluing it to the state. So that's going to now give me a new partial boundary manifold preparing my new state. Let me just mention that in this case where this partial boundary manifold is just some Euclidean segment of length beta, this operator O is just what we would normally call e to the minus beta h, where h is the generator moving along this beta direction. Okay, so regarding these operators, I want to make two comments. The first is that all of these operators commute with the operator z that I defined before. And that's again because the operator z act by taking disjoint unions, and disjoint union just commutes with everything. Therefore, these operators O must preserve the eigenspaces of the operator z, which are these alpha sectors. So these alpha sectors are not only superselection sectors with respect to these operators z, but also these new operators O that I defined. The second comment is that generically different O's are not going to commute amongst themselves. And you can see this quite easily using a picture. If you consider, say, stacking two partial boundary manifolds on top of each other in different orders, you're just going to get different results. So that tells us these different O's don't commute with each other, and the only way in which these alpha sectors can support these non-commuting operators is then for the alpha sectors to be greater than one-dimensional. Okay, so this is sort of a technical slide, so maybe let me ask it how much time I have. Okay, so then I'm going to skip the slide. Okay, we're going to now come back to the issue of observers in closed universes. So even though the pictures I've drawn so far are all of boundary manifolds and partial boundary manifolds, the whole point is that the abstract framework that I described can equally well apply to these newer prescriptions for including observers in closed universes. So on this slide, I'm firstly going to describe how that works for the Berkeley papers prescription, and then on the next slide, I'll also describe how it works for Misha and MIT people's prescription. Okay, so in this Berkeley prescription, the relevant cuts are going to be labeled by the observer type or internal state sigma. The relevant sets of partial sources are going to include elements which look like this. This partial source is comprised of a complete boundary manifold, which you can view as preparing a closed universe state, where this label J is going to label different possible boundary manifolds that you might want to consider. For example, exciting different matter. Attached to this is something which we'll call an observer half-world line, terminating at this cut labeled by sigma. Now we can construct a Hermitian form on these partial sources in sort of the obvious way, which is we take one of the partial sources and we just glue it to the star or the complex conjugate and time or orientation reversal of the second of the, okay, I guess it's the first partial source in this case. If we do this gluing, what we end up with is a boundary manifold with two components, Mj and Mi star, connected by a bulk geodesic, which is the observer world line. Now we can plug this complete source into the path integral, and the path integral is just going to sum over different bulk configurations which satisfy the required boundary conditions on these boundary manifolds and contains this observer world line. As I described before, this gravitational path integral can be viewed as computing an inner product, and in fact you can decompose this further into an ensemble average over different alpha sectors for the inner products in each alpha sector. Computing these gravitational path integrals, what these authors find is that the dimension of these alpha sectors can be greater than 1, but of course that's sort of what we expected from our general analysis. In fact, we can be a bit more precise. What these authors find is that these alpha sectors typically have dimensions scaling like e to the 2s naught in JT gravity. In fact, using our general prescription or general framework, it's possible to derive a bound from the positivity of the inner product, whose saturation agrees quite nicely with this result. So that's a nice quantitative check that our general framework actually does apply to this prescription. Now I can say more or less the same set of words for Misha and MIT people's prescription. Or, okay, I should say this is Daniel, Misha, and Ying's prescription. So in this prescription, the relevant cut is going to be given by the d-dimensional Hilbert space of some external non-gravitational system. The relevant set of partial sources is going to include formal linear combinations of states drawn from this Hilbert space with coefficients given by complete boundary manifolds. So this might seem very strange or funky, so let me break this down. These complete boundary manifolds have the interpretation of preparing some closed universe state, and the little j here labels different complete boundary manifolds that you might consider. For example, exciting different matter. The little sigma here tells you that this complete boundary manifold, at the very least, must excite some matter which constitutes an observer in the state sigma. This ket here denotes the state of an external clone which lives in this non-gravitational Hilbert space. If we then take this sum over sigma, the idea is that we're preparing a maximally entangled state between this clone and the internal state of this observer which lives in this closed universe. Now the inner product on this external Hilbert space gives us a nice way to define a Hermitian form on these partial sources. And to evaluate this Hermitian form, what you do is basically to pretend that these complete boundary manifolds are actually just complex numbers, and then you evaluate the inner product on the external Hilbert space. If you do that, what you end up with is some linear combination or superposition of boundary manifolds with two components, m sigma j and m sigma I star, with some correlation between them. Now, if we plug this complete source into the gravitational path integral, the gravitational path integral is just going to sum over different bulk configurations consistent with these boundary conditions. And in particular, it can include observer world lines which connect like this directly from the ket to the bra or to something else entirely. This gravitational path integral, again, has the interpretation of computing an inner product, which you can decompose into an ensemble average over alpha sector inner products. Now, computing these gravitational path integrals, what these authors find is, again, that these alpha sectors are no longer one-dimensional. But of course, that's, again, what we expected from our general analysis. Moreover, we can, again, be a bit more precise. They find that the dimension of these alpha sectors scales like the minimum of the number of observer states and e to the 2s naught in JT gravity. And again, this agrees quite nicely with the saturation of the bound you can derive from the positivity of the inner product. Okay, so let me just conclude now. I'll summarize by saying that we've now developed a fairly general framework which extends, again, previous work on baby universes, alpha sectors, and gravitational path integrals. We've used this framework to explain why one-dimensional Hilbert spaces arise when we consider closed universes, and how non-trivial Hilbert spaces arise when we consider universes with spatial boundary, and also closed universes with observers, using these newer prescriptions. In fact, by talking about these abstract partial sources, we see that all of these contexts are sort of treated on the same footing. Okay, let me now end by talking about some directions for future work. Recall that we define these operators O, which acts on these alpha sectors labeled by cuts. I think it would be interesting to extend this algebra of operators to some von Neumann algebra and try to use that to study the structure of the Hilbert spaces with observers. For example, previously Don Marolf and other UCSB people found that when you consider asymptotic boundaries, the two-sided Hilbert space, so this is the Hilbert space with two asymptotic boundaries, decomposes into one-sided Hilbert spaces. I'm not going to go into the details of what the mu and the different things here mean. The question I want to ask is basically, does a similar thing happen for observers? Does the two-observer Hilbert space factorize or decompose in some way into one-observer Hilbert spaces? The last question here is sort of just an open question. I don't really have a concrete idea of a calculation to do here, but I basically want to just understand generally to what extent the gravitational path integral can be understood as some random non-isometric code. To explain that a bit, in both the black hole context and these newer prescriptions for including observers in closed universes, people have talked about these ideas in terms of these non-isometric codes, which are supposed to map you from some effective field theory description to some more fundamental Hilbert space in which you're supposed to compute these inner products. In our language, these inner products are just these alpha sector inner products between states prepared by these partial sources. The randomness here just refers to the fact that we have this ensemble average over alpha sectors. So maybe one concrete question to ask here is, what properties of these non-isometric codes are held fixed and varied as we take this ensemble average over alpha sectors? Okay, so I think that's all I have to say. Thanks for listening.
Questions?
Is there any particular subtlety you expect in asking about generalizing this decomposition idea to the two-observer case? Is there a reason to suspect it's not a straightforward generalization, or is it just a matter of tracing through the details?
I think it's a matter of tracing through the details. For example, I think you already mentioned this to me, but you had some like continuity axioms that don't seem to have an analog in this case, like for the cylinder.
That might be an actual subtlety as opposed to a detail. Yeah, good, thanks.
Hi. So what I understand that the topology changing amplitudes are important for the analysis for both black holes and for this closed universe analysis. So, but if we go back to canonical quantum gravity, there are, when if I try to find some states, they should satisfy some gravitational constraints. So is like I do not see how the constraints are embedded in this. Like how the gravitational constraints are embedded in these setups when you also consider your topology can change. Mm-hmm. And so do you have a comment on that? Like,
I guess my comment would be that I expect the gravitational path integral to automatically impose those constraints. But I would also comment that I think the issue of constraints is sort of separate from this issue of why closed universes have one state.
Should not that state satisfy the constraint always? Like it's like finding the solution of the constraint. Isn't it the same problem? Or
I don't think restricting to solutions of constraints is what gives you this one state statement. I think the fact that we have one states for a one-dimensional Hilbert space for closed universes is associated with this fact that the gravitational path integral has this permutation symmetry for the different boundaries. I don't see that as being directly related to the issue of constraints on a fixed or a slice of a fixed topology.
No, I'm saying like, is there any way to impose this constraint for different topology or in a topology?
Oh, I see. Are you asking if there is a generalization of, say, the Wheeler-DeWitt equation to contexts in which you have topology change?
Yes.
I think that's an excellent question, which I don't have an answer to. I'm not sure if anyone has an answer to that question at this point, and I think it would be interesting to explore further.
Okay. And my second question is there any setup or calculation where these topology changing amplitudes are considered for, say, d equal to 4?
For d equal to 4.
Like rather than any lower dimensional models, is there any calculation one can do like to verify these things?
So are you asking if there are any concrete calculations
Yes,
for
one
a
can-
D equals 4 model, which to show that it satisfies the abstract structures
Yes,
that
yes,
I
yes,
talked
yes,
about?
yes.
I don't know of any.
Okay. Okay. Thanks a lot. Nice talk. Yeah.
So I have a question. So you mentioned this tension about the dimension of the Hilbert spaces, I think, right, in two prescriptions. And does this generalized framework somehow shed some light on how to resolve the tension?
I don't think, well, the tension is just an output of the fact that you're applying different prescriptions. So it's not surprising that you get different results in the end. What this general framework does isn't, like the goal of this framework isn't to pick out the right prescription. Rather, it's to isolate for you sort of the abstract structures which are giving you this non-trivial Hilbert space. So for example, if you're not happy with any of these prescriptions, you might try to come up with your own prescription. I think this general framework gives you some idea of what you might want to incorporate into that new prescription. Maybe let me give you an example. So after my paper came out, there was actually another paper about tracing, it's motivated by the idea that as observers, we don't have access to the whole universe, so they give a prescription for tracing out some environment. And they argue that this prescription gives you a non-trivial Hilbert space for closed universes. In fact, I think that prescription also falls under this framework. It's just giving you a different gluing rule, if you will. So I think this framework isn't really picking out a prescription, it's giving you a general framework in which you can, study different prescriptions on the same footing, if you will.
I also have a question. So when I was approaching baby universes using von Neumann algebras, I needed a critical assumption of having a very rigid sense of purity for a state to make it one-dimensional Hilbert spaces, and otherwise, even if the baby universe algebra is unital and commutative, it was not quite giving rise to be actually one-dimensional. So I was wondering what's the corresponding assumption that was used here to make that happen?
Okay, so I probably did not treat things as precisely as you did. Maybe can you explain more, like what was the problem that you were running into?
I wasn't running into a problem. It just, I was looking into when I was computing these baby universe algebras, and I constructed them using as like a discrete sums and unions that I could add on to. And we prove a very rigorous theorem that it's only of dimension 1, it's a Hilbert spaces, if and only if the state that I'm dealing with has to be in this particular sense of very restricted pure state, like so that its Gelfand dual is actually very, very well restricted and stuff like that. So I was wondering what assumption did you use to make these things to be like that? Because usually there is some assumption needed to make that happen.
I'm not sure I have a comment on that because I'm not sure I understand the question. Maybe we can talk more afterwards.
I strongly suspect it's the following, although we could all three talk later, which is at some point you said that you talked about an operator and it's a joint. What you really meant is an operator on its permission conjugate on some dense subspace.
Okay.
And there were various extensions you assumed to get simultaneous diagonalization.
Right, okay.
I think that's equivalent
Right.
to Monica's.
There's no other questions. Let's thank Vincent again for the nice talk.
So let me now ask you to come together and